The foundation of artificial intelligence hardware might be making a massive shift right now, trading traditional organic circuit boards for glass. The Chinese tech giant BOE, usually famous for making display screens, recently announced they have successfully built a massive, multi-layered glass core substrate meant for next-generation chip packaging. This complex setup features 20 distinct layers in a 9-2-9 configuration. Crucially, BOE claims this prototype has survived a battery of brutal reliability trials. This includes 1,000 cycles of thermal compression bonding, intense moisture checks, extreme heat and cold storage, and rigorous preconditioning. Now, let's be clear about what this actually means. This does not imply that China is suddenly mass-producing fully finished glass AI processors. It doesn't mean silicon is obsolete. And it certainly doesn't mean every copper wire inside your computer is going away tomorrow. What it does indicate is that glass packaging is officially stepping out of the concept phase. It is evolving into physical hardware capable of handling the intense physical stress of real-world manufacturing and daily operation. On top of this, BOE is putting together a specialized team to work on micro-LED optical interconnects built directly into glass substrates, a concept known as co-packaged optics. You see, the biggest hurdle for future AI systems probably won't be raw computing power. The real traffic jam will be the tiny copper wires trying to shuttle data between the processors, the memory, and the network. If glass substrates can successfully support bigger chip packages, thinner wiring, superior physical stability, and light-based data links positioned right next to the chips, they could fundamentally rewrite the rulebook on how future AI computers are built. So, did China just invent a 20-layer glass chip that kills off copper? Not exactly, but they might have just cleared one of the biggest hurdles needed to make that future a reality. Let's break down what BOE actually created. Today's modern AI accelerators are not just a single, simple square of silicon. A finalized AI product is a complex beast. It packs in several separate computing dies, tall stacks of high-bandwidth memory, power delivery, hardware, controllers, and data pathways. All these different pieces have to be perfectly placed, powered, cooled, and linked together with microscopic precision. The physical foundation holding all of this together is known as the package substrate. It acts as the critical middleman, sitting right between the delicate silicon chips and the larger system motherboard, ferrying power and data through thousands of microscopic electrical pathways. Right now, most top-tier substrates are made from organic materials. But as AI packages get larger and the internal wiring gets more tightly packed, those organic materials are hitting a physical wall. They have a tendency to swell, shrink, bend, or warp when they repeatedly heat up and cool down. And when engineers are trying to perfectly align incredibly tiny connections across a massive package full of different chiplets, even a microscopic change in shape can ruin the whole thing. Glass provides a completely different type of foundation. It stays incredibly flat, even over large surface areas. It holds its shape perfectly, allows for much tinier circuit features, and offers fantastic electrical properties for moving signals at blazing fast speeds. According to BOE, their 20-layer prototype utilizes a 9-2-9 layout. To put it simply, that means there are 9 build-up layers on top, a solid 2-layer glass core in the middle, and 9 more build-up layers on the bottom. The reason this specific layout is so important is that advanced chips desperately need dozens of pathways to route electricity and link the processors to memory and outside connections. Successfully building a massive 20-layer board that stays perfectly aligned and structurally sound is a massive engineering feat. This brings us to why these reliability tests are such a big deal. When a computer runs intense AI workloads, it gets incredibly hot, and it cools back down the second the work stops. Because different materials expand and contract at completely different rates, this constant temperature cycling creates massive physical stress. It pulls at the copper paths, the solder joints, the wiring layers, and the delicate areas where different materials meet. Intense heat can weaken the structures, while extreme cold can make them shrink and crack. Furthermore, the manufacturing process itself involves a lot of pressure and heat during assembly, long before a chip ever reaches a buyer. According to BOE, their prototypes managed to survive several standard industry stress tests. The headline trial was 1,000 cycles of thermal compression bonding. This specific assembly technique uses highly controlled heat and pressure to stamp down microscopic electrical links. Cycling through this process 1,000 times is designed to show whether the internal layers will separate, split, or lose their electrical connections under prolonged, real-world stress. The prototype also allegedly made it through high humidity testing, accelerated temperature trials, high and low temperature storage, and preconditioning. While these results don't guarantee the glass board will survive every single factory line or operational setting, they do prove a highly complex, multi-layered glass structure can stay functional after enduring intense environmental and manufacturing strain. That is a non-negotiable proof of concept before chip companies will ever dream of trusting a brand new material beneath multi-thousand-dollar processors and memory. This leads to a broader question. Why are these AI packages getting so massive in the first place? Simply put, a single sheet of silicon cannot grow infinitely large. As a single die increases in size, the risk of manufacturing defects skyrockets, making the chips economically unviable. Plus, current lithography machines have physical limits on how large of an area they can expose at once. To get around this, chip makers break down giant processor designs into smaller, specialized chiplets, packing them all together inside a single housing. However, this design trend shifts the engineering challenge away from the silicon itself and drops it right onto the package substrate. This baseboard has to connect all those separate chiplets with enough data bandwidth that they act seamlessly as a single, unified system. It has to stay perfectly flat, so thousands of microscopic connections line up without a single error, and it must support larger and larger physical sizes without bending out of shape. Glass is highly attractive here because it can scale up to larger formats than organic bases while maintaining much tighter dimensional control. Of course, using glass doesn't magically make things easier or cheaper. Drilling and filling microscopic vertical holes through a sheet of glass is incredibly difficult. Cutting large sheets of glass without creating structural stress points that lead to shattering is another massive hurdle. To pull this off, BOE states they had to develop a whole suite of custom capabilities. This includes high aspect ratio through glass via formation, deep hole copper filling, low stress metallization, multi-layer lamination, high density routing, and low stress precision cutting. These specialized processes are what turn a basic pane of glass into a highly advanced electronic platform. Now, let's talk about the idea that copper is dead. I want to be very clear. Copper isn't vanishing from electronics anytime soon. Even this new glass prototype from BOE heavily relies on metal wiring and microscopic vias filled with copper. Delivering power will always require highly conductive metal pads, and incredibly short electrical hops aren't going anywhere. The actual issue we're facing is a matter of distance and bandwidth. As AI systems push data rates higher and higher, traditional copper connections start burning through way too much power and struggle to maintain a reliable signal over longer distances. Electrical pulses lose their punch, create excess heat, mess with neighboring channels, and require crazy amounts of complex software trickery just to keep the signal clear. Inside a massive AI cluster, processors and memory are shifting mind-boggling amounts of data every single second. Sure, engineers can keep tweaking copper, but the sheer energy cost to transmit every single bit is becoming a massive headache. This is where optical communication steps in. Sending data using bursts of light allows you to move staggering amounts of information over longer distances with barely any signal loss and virtually zero electromagnetic interference. The tech industry already heavily relies on optical transceivers for major network cables, but the ultimate goal is to shrink those optical components and jam them right up next to the processor itself. We call this co-packaged optics. Instead of forcing a high-speed electrical signal to physically travel out of a chip, across a massive motherboard, and into a separate optical module, the light engines are built directly into, or right next to, the main processor package. By drastically shortening that initial electrical journey, you instantly slash power consumption while massively boosting your total bandwidth. So, why do glass and light make such a perfect pair? Glass is naturally suited for optical integration. It holds its exact dimensions beautifully, supports hyper-precise microscopic structures, and serves as an ideal dual-use platform for both electrical wiring and optical components. This is why BOE announced a dedicated team specifically targeting micro-LED optical interconnects alongside their glass substrate development. Now, you probably know micro-LEDs from high-end TV screens, but because these tiny light emitters are so incredibly small and fast, they are perfect candidates for firing short-range optical signals. An array of micro-LEDs could shoot massive amounts of parallel data across tiny distances. For an AI server, that translates to moving colossal amounts of data between neighboring chips while sipping barely any power. This is where BOE has a unique edge. They have spent decades mastering the art of processing massive sheets of glass, developing cutting-edge displays, and building micro-LEDs. Now, they are attempting to pivot all of that institutional knowledge directly into semiconductor packaging. Make no mistake, building a television and packaging an AI chip involve completely different tolerances, materials, and reliability standards. But BOE already knows how to handle large area glass processing, microscopic precision patterning, complex multi-layer builds, and massive automated production lines. BOE's strategic pivot highlights a fascinating industry trend. For years, display manufacturers have invested billions into factories designed to process gigantic glass panels with razor-thin films and perfect alignment. Advanced chip packaging is turning out to be an incredibly lucrative new outlet for exactly that type of machinery. BOE has already fired up a pilot production line for glass core substrates, claiming a capacity of about 1,000 boards per month. They've even started shipping out test samples to domestic tech companies, and some of those clients are reportedly already running heavy technical evaluations. But there is a massive caveat here. BOE admits this project hasn't hit full commercial mass production yet, nor is it bringing in mass production revenue. That is a critical distinction. Running a pilot line simply proves you can build the thing in a lab environment. It absolutely does not prove you have the competitive yields, the ultra-low costs, the massive throughput, or the final customer trust needed for the real world. In the commercial AI space, a single microscopic flaw on a substrate can instantly brick a package holding thousands of dollars worth of premium silicon. The real test isn't making one perfect glass board. It's churning out thousands of them flawlessly at a price the market can stomach. And make no mistake, China isn't running this race alone. Intel has been openly pouring research into glass core packaging for years. Every major substrate manufacturer, equipment supplier, and competing display giant on the planet is currently chasing their own glass breakthroughs. The global hunger for this tech is obvious. Every single AI company desperately needs higher memory bandwidth, more chiplets crammed into larger packages, lower power draw, and faster data links. Glass is an incredibly promising solution, but it isn't the only horse in the race. Traditional organic materials are still evolving. High-end silicon interposers are still the gold standard for ultra-dense connections, and advanced bridge technologies are getting better every day. Ultimately, the winning design will probably be a hybrid of several different materials, rather than glass completely wiping out the competition. What makes China's push so significant is their sheer scale of manufacturing. If BOE can successfully adapt their massive, panel-level display equipment to meet the insane tolerances of the semiconductor industry, they could start stamping out substrates on gigantic sheets of glass, rather than processing them piece by tiny piece like a standard silicon wafer. This panel-level approach could drastically increase output. However, larger panels also mean a much higher risk of warping, alignment drifts, and shattering. The economics of massive scale only work if the manufacturing yields are actually high enough to justify the effort. This brings us to what a 20-layer prototype does not prove. While passing these reliability milestones is incredibly impressive, a lot of massive question marks remain. BOE has not announced a single commercial AI processor shipping on this glass base. They haven't named a single customer, revealed a final package layout, shared their production yields, or given a hint about pricing or long-term field reliability. They certainly haven't proven that their glass solution is superior to every advanced organic or silicon alternative on the market. Furthermore, their optical interconnect project is still in its infancy. A newly formed research team is a long way from a finished, mass-produced product. When you hear phrases like "copper may be finished," it's best to understand it as a long-term direction rather than an immediate overhaul. Traditional copper connections are undoubtedly hitting a physical wall in the most demanding, highest bandwidth corners of AI architecture. Light-based links will likely phase out longer, faster electrical paths over time, but copper will remain completely irreplaceable inside localized power delivery networks and short-range interconnects. The real future is hybrid. Electricity will supply the juice, copper will handle local data hops, and optical links will step in to carry information across distances where copper becomes too inefficient. Glass could very well become the ultimate platform that allows all three of these technologies to live together inside a single, massive chip package. For China, this technology is a major strategic priority. Advanced packaging has become a massive geopolitical battlefield because boosting computer performance is no longer just about printing the world's smallest transistor. Today, an engineering team can stitch together trailing-edge chips, advanced memory stacks, and high-speed optical links to build an absolute powerhouse of a system. Advanced packaging doesn't make bleeding-edge chip factories obsolete, but it gives engineers an incredibly powerful workaround to drive performance higher. Because China faces intense international restrictions on importing advanced lithography machines and high-end AI hardware, the pressure to optimize every single millimeter of their domestic computing stack is immense. Breakthroughs in glass substrates, panel-level manufacturing, optical links, and chiplet designs allow China to wring every ounce of performance out of the chips they can make. In this light, BOE represents a very different flavor of semiconductor competition. They aren't trying to beat traditional chip foundries at their own game. They are crashing the party through the side door using their mastery of glass processing, display technology, and massive assembly lines. This cross-industry approach could provide China with a massive advantage if traditional chip suppliers fail to scale fast enough to meet the staggering demands of the AI boom. My take on all of this? BOE's 20-layer reliability milestone is a genuinely big deal, but we shouldn't let flashy headlines trick us into thinking a full-scale revolution has already happened. China hasn't magically replaced silicon with glass. Copper hasn't vanished, and a single pilot line pushing out engineering samples is a far cry from a mature commercial supply chain. What BOE has actually achieved is highly specific. They built a massive, immensely complex glass core substrate, figured out how to route intricate power and data pathways through it, and proved the structure can survive a brutal gauntlet of reliability tests. Crucially, they are tying that physical glass foundation directly to micro-LED optics and co-packaged communication. That dual-track strategy matters immensely because future AI clusters desperately need both physically larger packages and drastically more efficient data transmission. Glass solves the physical warping problem, while optics solves the data traffic jam. If BOE can figure out how to scale this combination affordably, China could position itself as a critical supplier of the infrastructure beneath tomorrow's AI chips, even if they aren't fabricating the core processors themselves. The true test for BOE won't happen inside a clean laboratory setting. The real hurdle is securing official customer qualification, driving manufacturing yields up, slashing production costs, and proving this technology works inside a real, commercially deployed AI server. So, what do you think? Will glass foundations and light-based data links become the undeniable bedrock of tomorrow's AI hardware? Or will the sheer nightmare of manufacturing complexity keep traditional organic boards and copper wires on top for the foreseeable future? Let me know your thoughts in the comments below, and make sure to subscribe for more grounded, no-hype coverage of the factories, chip designs, and engineering realities reshaping the global economy. Because the race for AI dominance isn't just happening inside the microscopic transistor anymore, it's happening right beneath the chip, between the memory stacks, and across every single pathway carrying the data.